Hello everyone. In today's video, I'm going to go over area and volume, what they are and why they're different. Before we actually get into the differences between area and volume, as you can see there's one point to understand. Things take up space. When you see a simple 2D shape such as a rectangle, we always see two different dimensions. So if I draw out my rectangle here, we're often faced with length and width. This gives us the border of the shape. Essentially, the dimensions are kind of, if this was a park, then it would be the fence. But area talks about something a little bit different, because between this, there's a lot of space, that the borders are kind of the park. And that is the area. Volume applies in the same way, but to three-dimensional shapes, which we'll get into a little bit later. So let's start talking about what area is. Space in between. When you have a two-dimensional shape, there are two measurements. That's why there's two dimensions. They are length and width. In order to find the area, it's a simple calculation when it comes to a rectangle specifically, or for any shape. Some variation of the formula length times width. Now, I know in shapes such as circles, there is no exact constraint as to what the length is and what the width is, but as long as you remember this simple way of finding out the area, it's better to find out what exactly the formula for that specific shape is. For example, if I start off with the basic rectangle again, I can assign it a length and a width, the perimeter. I will tell the length is 4 and the width is 3. So according to our calculation up here, the area is equal to 3 times 4, which is 12. As for units, suppose I had assigned 4 feet and 3 feet. Then I was doing 3 feet times 4 feet, so I'm left with kind of 12 times feet, which is 12 feet squared. Which makes sense because the 2 is kind of indicative of two dimensions. Because this is not one simple length, and this is not one simple width. This is everything in between. And since it's encapsulating both length and width at the same time, the unit needs to be feet squared. Suppose we look at something else. Suppose we look at a circle. Typically, we're given what's called the radius, which is from the exact center of the point to the outside rim of the circle. No matter where you look, the radius is always the same. Suppose I say that the radius here is 3. We're going to use the magic number of circles, pi, in order to find out the area. The formula for area is pi r squared. You can kind of think of it as the radius representing both length and width, and pi is what gives it the quality that we can use to make it the area. So I would just do pi times 3 times 3. So the answer is 9 pi. And if I assign a unit to it, we 9 pi centimeters squared. As you can see, even though technically on the circle we didn't do length times width, it's an important way to understand exactly what you're doing conceptually, because once you understand something conceptually, it's easier to understand how to do it in actuality. Volume is a little bit different though. There's a third dimension involved. That's why volume is known as 3D. 3D. We know length is one of them. That's not going away. We know width is one of them. But what's the third dimension? Imagine the same rectangle again. We're going to pretend it's like a piece of paper. Supposing this paper just has no thickness at all. If you looked at it sideways, you wouldn't see anything. But what if you had a shape that you could see something? Imagine I slowly add more rectangles just over and over again. Eventually, in this terrible drawing, you can see that a kind of depth evolves. If you look at, suppose, a book from the side, there's another dimension. You can look at the length of the book, you can look at the width of the book, but there's also the width beyond the width, there's kind of a height of the book, which is this, and that is the third dimension. Now you may understand why area doesn't involve that, because there was no width, it was just a flat. But if you look at the flat thing from the side, then you start to see what the width is and what the height is. So by that logic, we can say volume is equal to length times width times height, or sometimes you'll see depth. From the same principles that we applied earlier, if I had my length in centimeters, my width in centimeters, and my height in centimeters, then the unit for volume is centimeters cubed, just like centimeters 3D, because there's 3 dimensions that we're accounting for. Let's do a practice problem with that. Once again, this is the rectangle we saw from the last problem. We're going to put the same dimensions on it, 3 and 4. But this time I'm going to add in a little bit of depth. This is what's called a rectangular prism. And just try to imagine that there's an infinite amount of these planes just stacking into each other, and that's how you'll understand what the idea of depth is. And let's suppose that they stacked enough planes on top of each other that the depth is 2. By this formula, I'm going to say that the volume is equal to length times width times height. So the volume is equal to 24. And if this was in measurements of feet, like we said earlier, it would be feet cubed. A little bit harder of an example, but not too much. Let's take our circle again. I'm going to draw it like this. You'll see why shortly. If I have my circle and I start stacking them over and over again, eventually it would just form a giant tube. Then somewhere in the middle it would stop. That was really bad, but it's okay. So then I'd have 2 circles on top of each other and a bunch of little circles in between. The dimensions of this circle and this circle are the same. Suppose it was our circle friend from earlier with a radius of 3 centimeters. And we're going to say that the height was 5 centimeters. Well, first, what was the area of this part? It was pi r squared. Well, now I need to multiply it by how many circles we have, which is 5. So essentially we just did pi r squared h, which is the same thing because we said this is area, this is depth. So I'm taking my existing formula for area, multiplying it by the height of the cylinder is what this shape is. Pi r squared h. That's pi times 3 times 3 times 5, which is equivalent to 45 pi, which you could multiply out, but it's simpler conceptually if I don't. Centimeters cubed. That's what volume is. Now we're going to go over once again what the differences between area and volume are. There's different ways we can look at this. This is the coordinate plane. You might have seen this before when you're graphing. The x-axis and the y-axis. So if I draw my rectangle here, it's completely flat. All of the points are in the same area. No matter what point you go to inside this rectangle, it's all flat. It's all on the ground. It's flat. Area is essentially saying how much space all of the points in this rectangle are going to take up. With volume, we introduce a third axis, which comes in different ways depending on how you visualize it, kind of like this. This is called the z-axis. So try to imagine that this is another flat plane, if you can see that. And Slowly you stack it up infinitely on the top and infinitely on the bottom. By this logic, if I continue it, I can add depth, essentially what is behind the flat surface that we see when we're calculating area. So now not only am I trying to figure out what this side is, I'm trying to figure out what this side is, this side, and all the way in that space in between, and that is what volume is. So essentially, if I'm looking at a rectangular prism, if I'm finding the area, I'm just finding the space that one flat side takes up. But if I'm looking for what volume is, I want to know what the entirety of that cube is equal to when it takes up space. I hope you understand now what the difference between area and volume is. Try to look at it in different ways. Look at other formulas for area and volume, and you'll start to see the similarities about the length, width, and height. Thank you for watching.